Hello, 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 hello. वाईफाई नहीं है ये दिवस लाया जाए अरे दूसरा लेके आना दूसरा संग ये भी ले आओगे एडेप्टर रीसेट मार एक बार हेलो हेलो
आप सभी का स्वागत है आज के इस व्याख्यान के सत्र में। संस्थान की राजभाषा कार्यान्वयन समिति स्टाफ क्लब के साथ मिलकर जो भी सेवानिवृत्त कर्मचारी अधिकारी हो रहे हैं, तो उनका जो व्याख्यान, उनके अनुभवों का निचोड़ जो है वह हम सबको सुनाने के लिए जो है इस तरह के जो भी हम व्याख्यान है उसका आयोजन कर रहे हैं। तो मैं राज सिंह जी से निवेदन करूंगी कि वे कृपया आज के इस सत्र के बारे में बताएं।
धन्यवाद संध्या एंड वेलकम टू यू ऑल एंड सॉरी फॉर दैट हु आर स्टैंडिंग। एक्चुअली हम लोग बहुत कई सालों से ट्राई कर रहे हैं कि ये सेमिनार हॉल को थोड़ा बड़ा करें, पर कर नहीं पा रहे हैं। विजय भी खड़ा है यहाँ पे, सुन रहा है मेरी बात, शायद कोशिश करेगा कि इसको थोड़ा बड़ा कर दें, क्योंकि 700 लोगों में एक 100 की कैपेसिटी वाला सेमिनार हॉल कम पड़ता है। ये हमने कैंटीन में भी अरेंजमेंट किया हुआ है, बट आई थिंक वहाँ भी चेयर्स फुल हो चुकी है। टॉक का टाइटल आप देख ही रहे हैं। एक्चुअली अभी कल परसों संध्या मेरे पास आई, बोला सर सर ने टॉक तो भेज दिया है, अभी इसका हमें हिंदी भी करना है। टाइटल का बोला खाली टाइटल का हिंदी करना है। आप कुछ बताइए। मैं क्या बताऊँ, तो तब तो मेरी समझ में आए कुछ तो। मेरे को तो टाइटल का इंग्लिश समझ नहीं, यार तुम हिंदी की बात कर रहे हो। बट जो कपार टाइटल अच्छा है, आपको समझ भी आएगा, आई कैन एंश्योर। देश पांडे साहब बहुत अच्छे स्पीकर हैं एंड यू विल रियली एंजॉय द टॉक एंड आई विश के टॉक बहुत अच्छा है। इसमें ही विल एक्सप्लेन दैट फ्रॉम द बिगिनिंग ऑफ इनिशिएशन ऑफ द प्लाज्मा, हाउ इट थ्रू एंड what are the future of all these things. I think that for all the people, young generation and old generation, this will be a very informative talk. You will certainly enjoy it. Now I request Professor Deshpande to continue the talk.
Hello, can you hear? So, thank you for letting me into the seminar hall, and thanks to Raj Singh, Sandhya. ये टॉक एक मिक्सचर है, लाइक भेलपुरी. It has some history, it has some analysis, कुछ मनचाहा और अनचाहा advice. Generally, I would say something that you can enjoy after a heavy lunch with sweets. And given that the seminar hall is cool, I will gently remind you when the talk is over. So, what do we mean by Agni? In the true sense, it has a cosmic meaning which has to do with the transformative power. Rupantaran, that is supposed to be the role of it. So it transforms one to the other, and so what I mean by stoking is that it's already lit, and we need to add our samida, our havi into it to keep it going and to get what we want, because it is supposed to be the carrier. So,
ऑनलाइन पार्टिसिपेंट से रिक्वेस्ट है कि वे अपना माइक म्यूट कर दें।
so let me take you to the outline. I have 10 points to make. We have number of slides, and I will stop and spend time in something and might just zip-zap zoom through something that we don't want to. So let's look at creation. All of us know, and you are very familiar with this, Bharat Ek Khoj serial, famous Sham Benegal, and उसके जो opening lines थी, हिरण्य गर्भ संवर ततागरे वाली, जिसमें one mulls over the creation, and then the wording is ऐसे किस देवता की उपासना करे हम हवि देकर. That those are the taglines you can see. So this particular line is like saying that there was in the beginning this cosmic fire, and it was everywhere, and then there was nothing else but fire. So what is this fire? So I am drawn to this absolutely fabulous book, The First 3 Minutes by Steven Weinberg, and it's an old book, okay? After that we have lots of other evidences, but this is an extraordinary lucid account of how things unfolded. And so I'm going to go through this curious text here is something like this. What Weinberg does is he describes how the Big Bang unfolded. But then, you know, the time scale is very non-linear. At the very beginning, it was just a primordial soup, mostly energy, and even the fields had not really separated from each other. It was all a potpourri of everything. But then it rapidly cooled down, and as it cooled down, things formed. So what happens is that he takes a very innovative approach in which he says that I'm going to divide this into frames, and each frame is 1/3 of the temperature of the previous, because that's how you can describe things. So I'm going to take his first frame. This exact text from his book, okay? So I'm not bringing any wisdom. You're just showing you what I am fascinated by, rather than I am trying to tell you something. So the first frame is 100,000 million degrees 10 to the 11 Kelvin. You take 4 out of that, so that is 10 to the 7 EV, that's 10 million EV. It's not a big temperature for plasma phases. Routinely runaway electrons get there. But this is all the universe having at 10 million EV. So the universe is simpler and easier to describe than it will ever be again. This word is very important. And you will see this word again used in the astrophysical literature, because one quantity, temperature, describes everything, especially when things are in thermodynamics. So what is happening is that it is filled with an undifferentiated soup of matter and radiation. You cannot distinguish anything. But go toward the end, you will see the contents of the universe are therefore dictated by the rules of statistical mechanics and do not depend at all on what went before the first one. Very important sentence. Okay. So it's frame by frame, but each frame is kind of independent of the previous. And all we need to know is the temperature is 10 to the 11 K, and the conserved quantities, charge, baryon, number, electron, all very small or zero. So nothing is formed in this first frame. So let's go to the fourth frame, because there are lots of things in between, but I'm coming to fourth frame because there is something very interesting here. 13.82 seconds have elapsed since the first frame. We are now below the threshold temperature for electrons and positrons, so they are beginning to rapidly disappear as major constituents of the universe. They are getting combined into atoms. So now only ordinary helium is tightly bound nucleus. So as I said, it can indeed hold together at the temperature of the third frame. However, tritium and helium-3 are much less tightly bound, and deuterium is especially loosely bound. It takes only 1/9 as much energy to pull a deuterium and nucleus apart. So at the fourth frame, temperature is 310 to the 9, nuclei of deuterium are blasted apart, not this, blasted apart as soon as they form. So they just go across, they have no time, and there is no chance of them getting destroyed. So this is the first fuel that we got at 13 and a half, let's say 14 seconds for the fusion. So one of the fuel part is ready. Now let's look at the stellar fire. What happened to the other, other fuel, other parts? We just see now. The stellar fire is three important people here. Harold Urey discovering deuterium, which we just saw, but it took a while. Then heavy hydrogen is deuterium here. Hans Bethe for the theory of or explaining how the stars are powered, and George Gamow to tell us why a repulsion was actually overcome, how it was overcome by quantum tunneling. So unless this last thing is there, we cannot explain anything. Although Gamma's theory is more about how an alpha particle escapes a nucleus, the same thing works for something getting in. The guy who gets out knows how to get in also. So, but of course there are many zillions of rattlings between the nuclear wall until it finds a way out. So it's a very low probability, and luckily it's a low probability, because if it were a high probability, most of it would have been over by now. So this is a famous paper that every student, everyone must know and read. And this is a complete paper in which, I mean, there were very few after that in terms of its completeness. So Bethe worked out everything. He was, remember, you must have seen his, in the movie on the Oppenheimer. So the important sentence here is that the carbon-nitrogen reactions are unique in their cyclical character, which we will see later. For all the nuclei lighter than carbon, reaction with proton will lead to the emission of an alpha particle, so that the original nucleus is permanently destroyed. Notice this again, lighter than carbon. Okay, so what is happening is that as soon as it forms, it gets destroyed. As soon as it gets formed, it gets destroyed. So who created these lighter elements? Lithium, boron, beryllium is a question, and we will see its answer too. So if we look at the picture of the binding energy curve, which you know very well, that as we add nuclei, until iron, you have a positive return on investment. After that, you have to spend energy to make those higher nuclei. So, but if you see the cosmic processes, and you can see here, so how do you get to that? Anyhow, so you can see the color coding, but notice the beryllium, partly lithium, beryllium and boron coding. And so you can see that the dying low mass stars, and particularly the cosmic ray fission, was responsible for manufacture of those elements. Multiplier, neutron multiplier, and our breeder. In fact, most of it is made by various types of stars, and the merging neutron stars do a pretty good job in all the higher manufacturing with dying low mass stars. So every stage, the cosmic fire, as it is offering itself in creating these elements. So when it was found that such a thing happens, that there is a thing called fusion, it can work well, people had started already thinking about it. This is Bhabha's address to the IAEA General Assembly in 1955. You can see in 1964, the ICTP Nobel Prize founder Abdus Salam. You can notice the flag of the United Nations there. Notice the year also. The year relates to the Cold War. So under that flag, there are this place had scientists from America, Russia, all together, and to an extent. Could you mute, please? Hello. So where people who were not sharing information with each other had gathered and were exchanging, and of course there was a few years before this thing we had already been shared, like Tokamak. There was a team from there was a Russian submarine on which Artsimovich and other people traveled to UK, and they actually exchange in the UKEA. They exchange notes, arrange visits. The UK had developed a laser diagnostics for temperature. This was used in, I think, TM3. So there was a lot of active thing there, and the Russians had already reached. In fact, in TM3, you can see the DD fusion, TM3. Okay, so we are dealing with something like 60s and 70s here. So and a star here was Dr. Vikram Sarabhai, who not only conceived the space program and established a number of institutions, but had also the seeds of the fusion program. So this dream didn't need anything. It was so exciting to make this source, tap into this source and develop this source. Of course, there were other, there were political things, like you might remember a letter by John Dawson to the president of US, where they mentioned the difficulties of funding in fusion and why US must invest significantly in those times. So there are very interesting facts there. Now let's come back to our good old stuff here, DT fusion reaction. Now, this I am saying because you already know all this, but there are still some people here who might be new and might just like to sync with us, so don't be offended. So we have deuterium and tritium nuclei merged to generate a neutron and helium nucleus. This releases 17.6 MeV. Its abundance is there in the oceans, so it can be taken from the sea, about you can say 10⁴ liters. It gives you 1 liter. Tritium was detected in 34 in DD reactions. It's a rare isotope, but it can be made, and it can be made from lithium. If you just leave it to itself, there's a half-life of about 12.5 years actually. It converts into helium-3 by emitting an electron into neutrino. Here is this is how this dynamics gets played here. I have written these DT reactions in such a way that it's easy to see 2 plus 3 is equal to 4 plus 1, so you can just cancel out in integers there. And what matters here is the 006 of tritium, because you have now 3 nucleons bound together, so you have already a good store of energy, and so the net is almost, I think, about 2% of the proton mass, which gives us 17.6 eV. So this is just a way to represent that. Nuclear fusion in the sun proceeds a bit differently. I have a comparison table coming up ahead. So hydrogen fuses with hydrogen to produce deuterium, which fuses with one more hydrogen to produce helium-3, and then the helium-3 undergo fusion. So that cycle has total 4 hydrogens consumed, but actually 6 ones participate and 2 are released. The energy is 26.7 MeV. In the lab, you know very well that we can use this neutron to regenerate. Now, where is the question of urgency here? I'm going to jump back in time here, jump ahead in time, and I draw your attention to a sentence by Dr. Kakodkar in 2019. So if you see the last sentence here, this speech was at the time of the cryostat, one of the cryostat milestones being reached. And you notice that he says that fusion must be available before the world reaches the cliff edge. Now this means that we recognize at all levels that there is going to be a problem. It's just far away. So we can always say, I don't have to solve it. But then the point is that it is heading towards a cliff, and the fusion has to appear on the horizon fast enough so that all its problems are actually solved, and it actually becomes a viable source, because it's going to take a lot of time. Even fission reactors took a lot of time to get to that point. And even after making the reactor and connecting it to grid, you still have to wait for about 100 days until you get it at a commercial rate, because they go through a lot of grid code, tests. So let's ask, what will the next generations think? Okay, this is an important question. So what do I mean by that? So let us look at another absolutely fabulous book. We are used to seeing Francis Chen's book on plasma physics, but take a look at this. So what I'm showing here, again, this text is from his book, the one above, okay, just below the figures. So what are those two figures? First is the Keeling curve of the CO2 concentration in the atmosphere. This comes from the Scripps Institution of Oceanography. You see the year 1960 to 2000. There's a steady increase in the CO. And the key point was that, is the CO2 increase responsible for the rise in temperature? Okay, so the next curve is the rise in the surface temperature, okay, and it's taken from the IPCC Intergovernmental Panel, which does an extensive study. There are more than 600 people all over the globe who go through reports, analysis, teams of people working on that. And so you can see the last stage there, where you can see the rise in temperature. Okay, it's half a degree. Now, first question is, are the graphs related? So the answer is now, but Chen says that after a lot of analysis, this I'm showing you just a glimpse, but there's a full chapter dedicated to that. Is the man responsible for it? That means yes, the burning of fossil fuels is an answer, clear answer. And so there is a lot of analysis in that book, so I'm going to skip that. So the key point here is that it is not just a tiny rise in the average temperature. It takes a while to understand the import of those sentences. And it's actually like pulling a supporting pillar out of a delicate physical, chemical, biological, and environmental ecosystem. There are several examples which are stunning. For example, there are significant changes in the biological life cycle of, let's say, fishes, insects. There could be changes in the viral composition and the bacterial composition. There could be a change as big as changing the Gulf Stream, which actually is responsible for a number of warm water and cold water currents around the globe. So there are a number of changes which can happen in human life much before the level of sea rises, although the level of sea is already rising quite a bit. So this is one thing. So there is a problem. First thing is to recognize that there is a problem, because this is one of the first steps in solving it. Otherwise, we don't have much progress. Now, here is an absolutely fabulous picture. Actually, it is taken from Professor Kao's talk. It was delivered in 2003, and this was Kumari L. Meena lecture, I think, in Palghat. There's a foundation there. And so this is not there in his paper. If you download that paper, you will not see this, right? It's there in another write-up of his. And what is this? This is actually a cartoon by Sheffer in 1988. And Professor Kaur aptly chose this. Now what it shows you is 5000 BC, okay? The left hand side is 5000 BC, right hand side is I think another 5000 BC. Okay. And so what you see there from the Sphinx to this population on, let's say, moon, this hemisphere is representative of a very futuristic colony on the moon or Mars, whatever you like. In between there is a blip. You can see the rise and fall. And that is the period over which we would have burnt out all the fossil fuels available on Earth if we were able to do that. And that would have, of course, wiped us out also, but that's okay. Just to show you that a fossil fuel era is this. And this era will end, naturally end, because now you can see, you saw how difficult it is to negotiate. You saw the COP negotiations, the fact that people are saying that the developing countries should pay for the cleanup, okay? So there, and how much money, you just see the amount of money that they are asking. So you see, there is a deadly combination of geopolitics, people, their aspirations, swarth, and of course all is lined as if we are cleaning the earth. So it's lined towards Paramarth, thinking that everything is very beautiful, you just pay us the money. That kind of thing will happen. And that will continue to happen until you are technologically strong. Otherwise, you will end up signing only one-sided agreements. So I have, this is a very fond memory for me, because Srini gave this talk and I borrowed some slides from him, and I still remember him very much as a strong group member and then eventually a great colleague. So Srini had made this slide in 2009, this is still valid. Actually, I and Srini were invited to a review by a PhD student in IIM. The guide was Dr. P.R. Shukla, and I don't remember the name of the student, but his reference is somewhere here. And the year was 2000. And Thomas Hamachar and one more person from Germany had come to IIM. In fact, they didn't come to IPR. Okay, so no one knew. So we had an invitation from P.R. Shukla, Professor Kaur forwarded to us, and we went there for review. So it was a very nice presentation, and at that time, Shukla and his student were trying to see what would ITER do, 2000, okay? I'm referring to 2000. So how would ITER become safe in future, a fusion reactor, and then our ITER will, let's say, become a basis for a fusion reactor, and then how that fusion energy will penetrate into the society. Will people accept it? Will they buy it? What will be its cost? Those are scenarios, and they're mute, please. Okay. So the thing is, his inputs were important and were going to be taken by the planning commission. He was on the body of the planning commission, and he was preparing these inputs. He had students working on that, and this was a very nice exercise. So at that time, let me tell you this as a sideline. At that time, he showed us a very fascinating paper. It was from the proceedings of the Royal Society of London, and this paper's date is 1900. So this paper is 100 years behind that. And what was that paper about? कि लंदन के रस्तों से घोड़े की लीद कैसे निकाले? Why? Because we never thought that that we will ever do without horse carts. Okay. So, and there would be so many horse carts after 100 years that the streets will you will have a real problem with the horse done. So while you are working on the steam and the other coal and other cars, they were expensive, they looked fancy. We also thought electric cars will never work, right? So in our times, I'm telling you, now you see everywhere. So the point is, technology, markets, people, and this whole game works out very differently. It's very different compared to what a scientist can imagine by extrapolation, by 3-point extrapolation. It will not work that way. Today something looks expensive, tomorrow it will be, we don't know what it will be. I mean, take for example, another example is कि कैलिफोर्निया के डेजर्ट, लेट मी टेक दिस टू हिंदी. कैलिफोर्निया के जो रेगिस्तान है, उसमें एक सब्सटेंस मिला था कई साल तक, टोटली यूजलेस, ना इलेक्ट्रिक कंडक्टर था तो वायरमैन आगे काम का नहीं था, ना इलेक्ट्रिक इंसुलेटर था तो वायरमैन को प्रोटेक्शन के भी काम का नहीं। बट फेयर चाइल्ड डिड नॉट थिंक, वो प्रोफेसर ने उसको भेजा, वो सिलिकॉन था, नाउ सी वेयर इट इज। सो द पॉइंट इज, it is important to notice the potential of something. It looks very ridiculous, it will look very expensive, it will look very unfeasible, but you still have to see its value. And its value lies in the transformative power. And that is why the name, this primordial fire. The power of an invention is to transform the lives. So here, what you see here is that if you were to get 10% contribution from fusion, let's say in future, okay, very far in future, will that start turning the curve downwards for, fossils and other things? And these were projections, but what is important here is that there is a limited potential of resources, fossil, gigawatt electric year. 7614 means what? It means that if you took 1 gigawatt, it will last for 7,010 years. But we need almost 200 gigawatt. Okay, so try pulling out 200 gigawatt out of that, you will see how many years it will last. So renewables are 102 gigawatt every year, but they are available every year on year, no issues. In nuclear and thorium, you can see the fabulous amount we have. So if we develop fusion, if we have fusion neutrons, if we can take it to the third stage in an accelerated manner, it will be great. So now what do we need for a sustainable growth? So I am coming back to a paper which is this year's April. Okay, this year's April. This is by Dr. Grover. And look at this sentences here. See, what we are looking at is a composite quantity called Human Development Index, HDI. HDI is defined, well known, you know it very well. There are so many curves of HDI drawn against electricity, per capita consumption, primary consumption, and so on. But the key point is HDI is representative of the overall health and wealth of a nation. If HDI is high, then generally the longevity of the people is high. Their access to medical care is high. Their general difficulties which they might be having. A large population suffers today from malnutrition also, because it doesn't even know, what is good nutrition. So if you put all it together and just call it as an SDI, then the target of, India is 0.9 by 2070. We are at probably 0.6 or something, and there are so many statistical studies which tell you if you do it this way, what is. But broadly, we are not there at 9. And remember that a number of ITER partners are already at 0.9. Okay. Then, the final energy requirement, which is 18,900 to 20,000 terawatt hours per year. If you want to convert it to units, then the TWH will have to be converted to BU or billion units. Just multiply by that a little bit with another factor of 3. So, but this is an indicator of where we want to be. And there is a certain amount of energy, about 4,400 or so, which is required for creating hydrogen. So now what are we looking at? We are looking at what we have tried to commit. Remember that there is a thing called NDC. Many of you may have heard, many of you may not have heard. NDC is called Nationally Determined Contributions. These are commitments made by India at an international forum on what we will do to cut down carbon emission, how we will improve efficiency, how we will cut down, and if at all there are some things which are emitting a lot of carbon dioxide, then what will be our strategy in absorbing, sequestration, or reuse? What do we want to do? That is decided, and one is trying to stick to that. So if you go by those methods, you can see that to leave a better earth behind us, there will have to be a significant effort in jacking up the power scenario. You can see this is a download I did on 5th December. This is a live thing which comes from the Central Electricity Authority. There's a big dashboard. You can download things. You can make your own charts and analysis. What I did was I just looked at the total capacity, not even what was consumption, and it's 454 gigawatts. Okay, 454 gigawatts is the installed capacity. You might be using sometimes less, sometimes, and it's seasonally varying. But where is the contribution? You can see a significant change in the solar power, almost 20% installed, and we have a lot of dependence, 53% on thermal power. And also, remember that this does not include the whopping $137 billion oil import that we have to do for primary use. So we are incredibly dependent on a few countries, few privileged countries, because of our growth and because of their possession of the wealth, which is in asterisk called black gold, and it's actually black gold. So what is an important sentence here is meeting the twin objectives of decarbonization and economic growth. If you want to grow at a certain rate, then you have to have a rate of producing energy, but you don't have resources, so you will have to burn carbon. So you will be fighting a contradictory thing. You want to decarbonize also, you want to grow also. So this was a challenge which Dr. Boaz very nicely captured in his, there's another paper by him 2 years ago. So look at the situation. Target is 24,000 TWH per year with HDI 0.9. HDI will happen only if you have good infrastructure, you have lots of industries, people have jobs, etc., etc. And per capita income, per capita consumption of 16,000 units, which means not by the person, but by a total pro rata on that person of his industries, agriculture, transportation, everything put together. But where are we? We are at a world average of 3,000 units per year. This is a world average. And India is at 1,000 units per year. Okay. So this 1,000 units per year per head means if you divide by 12, it's kind of 80, 90 units. And every month, every 2 months, you get an electricity bill. So that if that is true, then it should have been 160 units, but that is not true. If you have, a couple of fans, microwave, fridge, washing machine, you will see an average of around 350 units every 2 months. And so this is way beyond a decent living that a large number of here are privileged to live. Okay, so you can see where we stand. Now, this is something straight from the government. This notice this site. Site is PIB. This is Press Information Bureau of the government. Cabinet's decisions are reflected on the PIB site as soon as they are made. So what do we see here? This is a launch of a report on how do we achieve those targets. There are several trajectories. You could go this way or that way and try to achieve these net zero targets. And there is a study that has been launched. And you notice that critical minerals are also a major problem for us. It's not just energy. A large market is captured by some countries whom I will not name, especially rare earths, etc., tungsten. So all critical materials are captured by them, and they sell it at such a rate that it is impossible for the other industries to survive. So, and of course we also do the anti-dumping, but that's okay. So there are this official that you have to meet this side. Now, how do you do that? You have so many ways, and there is a certain let's say effort in each direction, and you have to make use of every possible resource. That's there in the paper also. That's our position also, and that's there in the paper. Let me come back to what we know is a potential solution. So if we look at the history of coconut, this is a cartoon from Boris Kadam shows famous paper in Plasma Physics and Controlled Fusion, 1988. And so this paper captures the historical evolution of tokamaks. And so this is what you see on the right is Artsimovich thinking over what could be various ways of confinement. You see a very nice drawing of the mirror and the commemorative stamp launched. Artsimovich was an extraordinary champion of this, and he in fact said that fusion energy will be realized when the world actually demands it. Okay? Because he saw the rise and fall, and he was sad. He said that no one seems to care for the immediate, but only when you need it badly, then you will see its importance. So let's come back to some physics now. So we need to note that the very act of confining the plasma throws it out of the thermodynamic equilibrium. It's a catch-22 situation. You want to use it, but it throws out of equilibrium. So then the plasma devises its own ways to escape the trap. Various instabilities, gradients, and waves help it to achieve its objectives. It escapes rapidly, and it continued to do so until people found more clever ways and tried to satisfy it. It's divide and rule type of thing, like separating ions and electron turbulences and understanding the time scales on which they respond collectively. So finally, the third bullet is that how dense and how hot the plasma should be, and how long shall we confine that to have a meaningful energy output. Because ultimately, what matters is a dense hot plasma for a sufficiently long time. That's it. Now, how do you get there is your problem. So the way to do that is, of course, through the fusion triple product. And so NT tau in units of 10⁻20 and kilo electron volts in seconds if we measure, then around it should be 40 or so. So let's take a look at, we often encounter this, so let me just show you, if we look at sun as a power plant, what does it mean? So you see we have almost 8 orders of magnitude size as far as the reactor size is concerned. The fusion fuel is HH and DT there. Energy is about same, 2717. Confinement is gravity, on that side is magnetic. Density is extraordinary, 150 grams per cc in the core. One bottle distillery of sun will weigh 120 kilos. In the reactor, you would reach almost a nanogram at best per cc. Then you have 10 to the 12 seconds as confinement time, because a photon which is emitted in these reactions, the gamma photons, it will take almost 1,000,000 years to come out because they rattle around in the center for a long time. This tokamak would be about 3 seconds. Power generated is 3 × 10⁻26, and you have 10⁻9 here. Power flux at the exit surface is 60 and 2, which is interesting because there is not so much difference there. This is because 4 pi r square division. Fuel is preloaded in the sun, no issues. We have to recirculate it. Ash removal is no need in the sun. It continuously goes to the core and it becomes the fuel for the next stage. So the sun has solved its problems. The helium has risen from 24% when it started at the very beginning to now 60%, but still no problem. You 60% dilution in the core. Of course, this is a situation which is extraordinary because everything plays a role there, and so we need it badly. Ash removal. Lifetime is 10⁻9 years here, and it's 50 years. Next 10⁻9 years. So we have 10 billion total years. Let's go back to tokamak. So in thermonuclear fusion, the charged particles will collide with each other because they are trapped and they are moving randomly. And particle velocities obey a certain distribution. So scattering will be the most probable outcome, but every now and then, based on the cross section, the fusion reaction will happen. The top curve there, the DT cross section is higher. These numbers are taken from a report, just for your reference, but this is a high number, and that's the only, at 10 kV, that is a reasonably economically acceptable reaction. At higher and higher temperatures, we have lots of trouble with synchrotron radiation, cyclotron radiation, and other losses. So, as far as the confinement is concerned, we use magnetic forces. And if you take an example of a 1 keV deuteron moving perpendicular to 1 Tesla magnetic field, its radius or orbit around the magnetic field will be a couple of millimeters. But they can fly along the field. So if we were to make a circle and let it go around the circle, it will come back to its tail. So the only problem is then if it drifts slowly across various circles. And that problem has been understood, can be solved, and can be solved by making the circle helical, and not just go round like this, but go helical. And that way, on an average, the particles don't go out of the. So it is one of the best confinement schemes that you can imagine, but it requires a current inside. And so I have not covered here the inertial and decelerator. So the confinement scalings have continuously improved over many decades, and data from many tokamaks, including high field tokamaks like Alcatel CMOD 8 Tesla to low field tokamaks, various types from diverters and non-diverters. It has grown and reached a point where one is able to at least do a good engineering scaling. So on the x-axis is the, let's say, prediction based on the major radius, minor radius, toroidal field, and so on. Whereas on the y-axis is an experimentally found confinement time, which is found by, first of all, letting the plasma reach some kind of a steady state so that its energy is no longer changing with time. So dW by dt is 0. And at that time, taking the ratio of powers, we can find this. So the generation of neutrons is known. It is, you can see this is T4 1971. So DD neutron, but it's an arbitrary unit, but it's there. And it's quite small actually in the beginning. You can see T3, T4, or max. So when they did the DD shots, it was the neutron production has gradually increased, confidence has increased. So eventually you can see these important shots, the final shots, ending shots fired in PFTR and jet. And you already know the first breakthrough in 1994 and then 1997. The graph here shows you a composite of PFTR and jet previous shots and how these shots, how long have these shots produced the neutron pulse. And what is interesting is you should see the capital Q there, which is 0.65 and 0.2. What do they mean? They mean how much power we produced and how much power we put in. But this is actually obviously not really true. It is an equivalent of QDT because this was a, wherever there were certain DD shots, so they're scaled to DT. So that had there been DT, this is how it would have been. But these ones that you see are real DT shots. So the progress of the NT tau has been going towards reactor-like conditions. It's just that it is not there. There are, you can see several circles there, half circles, which are basically QDT equal to 1, whereas ITER aims for QDT equal to 10. And so now coming back, I mean, having now known this uh, it's time to find out, you know, what should we be doing, and where are we coming from, and where are we going. So I will go into some of the slides which were compiled by Professor Sen in the Aditya 30 years, and it's important to look at them again. So how did it all start? So I'm now coming back to Dr. Sarabhai's vision, and so a faculty meeting in PRL, and how Dr. Sarabhai outlined the plan. I'm trying to tell you where this program has its anchor, where has its root in the historical past. We are going back something like 50 years back, okay? And so uh, he has his own way of saying it, very nicely said, and it's a wonderful talk. So then under the leadership of Professor Kao, a program started in PRL. So in PRL, there was a thing, it was called PPP, it was called Plasma Physics Program. It was created under the DST. There were at that time something like some 11, they were called HPTs, HPTA, I think, high priority thrust areas. And one of them was superconductor, other was lasers, third was plasma physics, and there were a number of them. There were some other areas too. And so PRL had then taken this program up, and we were given, or rather I was not there at that time. It started in 1982 actually. I joined in 1984. So there was a 5th floor in PRL. There were seven floors. Each floor had a program. There was planetary atmospheric science, there was paleobotany, there was high energy physics, there was astronomy, there was upper atmospheric mapping program, and there were a number of others, and this was a plasma physics program. There was also a cosmology and astrophysics program. So this 5th floor was very interesting. This was all one had. So if you look at this, the architecture of PRL, you will see a long corridor with two very big halls at the end. Those were the experimental halls. And then there were offices in between, maybe about 7 or 8 offices on both sides. And so that space was obviously not enough. So the team that time was thinking of creating a lab. So they built a lab. It was called Beta Lab, because I think Professor John had visited one of the lab in the US, and he saw, there's a photograph in his blog. He saw a beta-like structure being made, and then I think Professor Kao and these people must have thought, why don't we make it ourselves? So let's start experimenting with the torus as early as possible. So these were the times when, and 82 was also the time when I think Aditya proposals must have been getting developed. Because I was a student then in 1984, and I remember that I had coded one of the magnetic field calculation programs and shown it to Dr. Saxena, and he was pretty impressed with it. So I think he also showed me his calculations. It was very interesting. We just walked into his office first year. So this was an exercise given to us. And so that time there were a lot of activities like double plasma, then mirror-like plasma, multiple coils plasma, straight, then bouncing particles. There were lots of experiments there. And there were a lot of theory with Dr. Sundaram, Professor Sen, Professor Kao. I don't have a picture of Dr. Mattu here, unfortunately, but he came from the radio astronomy, and he joined that group, PPP group. And so, interestingly, when there was an advertisement in the newspaper that those who want to apply for PhD send a letter. So I mean, I also didn't know. I just wrote an inland letter. Can you believe that? I wrote an inlander saying that I have done these courses, classical mechanical rejection, etc., and I would like to appear for interview, and it came. So there was nothing, no photographs and this and that. So when we came and went to PRL, the PRL's person, the interviews of PRL were also planned on the same day. So there were 3 of us from Nagpur and 2 other places. The so PRL person, academic committee person came, and he said, "Would you like to apply for PRL interview also?" I said, "Yes." So fill this form also. So so we finished one interview, second interview, and it was over. Then after some time, I received a letter from plasma physics program that we would like to offer you. And so I said yes. Then after that, PRL letter came. So then I didn't know what to do. So I wrote to them that, can I say no? So those interesting. And so then we joined there. And that time, there were very interesting developments. Maybe I will cover certain anecdotes and incidents on the day 31st, because we will reserve for that. It will divert this our discussion. So this transition took place. This is the PRL, and this is today's IPR. Of course, it has a different look because of this thing. And at that time, uh, there was this was a big discussion at that time, that Professor Kao is going to, he's IFRC chairman, he's going to deliver a lecture, etc., etc. And he did make a case, because I remember many years later when I met Gunther Mang in the IAEA, he remembered fondly Professor Kao and said that I was absolutely stunned at the passion with which he pleaded for broadening the ITER collaboration network and pursuing that. So, so in the early days when this whole thing started, if you really go back, you can see the fundamental investigations and ionization equation. But leave that aside. There were other developments in creating a vision for fusion. So this is the early experiments on the electrojet. The electrojet is a very important index. It's called auroral electrojet index. I think it's also called AI. Luckily, so that index is an indicator of oncoming geomagnetic storm, and it can tell you. So there are a lot of analysis of that index, and there are instabilities which were of interest then also and now also. And so these were then simulated what kind of instability must be triggering this. So these were the early experiments. This from the Professor John's archive. Then there were papers on that. And that time, this few decades ago, this was some kind of a distributed picture like this. And SINP tokamak also pitched in with ultra low Q discharges at that time and new diagnosis. There was a exchange of people and ideas at that time. This was old structure of IPR with lots of water, big water body. This was actually the if Ajit is here, this was the heat rejection system for the IPRs, and there were fan coil units in each room. And so these were actually the cool. There were fountains, and there were these big gaps that you see between the plinth and the pipe. There were holes there, large holes for the pipes, and we have seen the wire-tailed swallows making nests there in those times. They were very nice swallows, bluish colored swallows with long tail and like a racket-like end at the end. Of course, later on, we never saw them later, but then IPR also evolved. The experiments in 1986, which means now we are here. On 23rd April 1986, we moved here on a very hot afternoon. There was one bus which carried all of us there. And Professor Kao came in the car. And then we were all in the queue, and Professor Kao asked me, Shishi, do you know who is that person? Because there were very few of us, so we were standing in the queue for lunch. So I said, he's a new join, Mohandas. So Mohandas's first day was when it was here. Okay, so that was very interesting. So then, of course, they met, and but that he could spot. in that family, in the family, there's one person new who's joined it. He joined us in the bus directly, actually. I remember that. So, in then there were experiments on so this is the first brush with dynamic tokamaks or RFPs or FRCs, you might say, the rotating relativistic electron beam experiment with KKJ. Now, why this is important is because this was the beginning of Professor John was extremely creative. If you sometimes get a chance to talk with Harish Pathak, do talk with him. He will tell you the stories of how they designed the diagnostics, how they fabricated some of the insulators also using araldite. But here, this is the time when high voltage experiments and high vacuum are coming together, a deadly combination. And then eventually, this linear gave way to toroidal with Dr. Chenna Reddy and John. This lab was here, as you know, Beta Lab. And so this growth continued at a great pace. And we have lots of, I don't have the pictures of all. I'm sorry if I missed some experimental facilities here, but whatever I could get in the past, I have just put here. So it continued at a very furious pace. And there were a number of facilities which got developed in the other following 2 decades. And the activities also expanded from, various aspects of physics to even certain complex systems, quark gluon plasmas, pure electron plasmas, and so on. So, and the portfolio expanded to transport, to waves, to instabilities and turbulence, in which both experiments and theory and simulation continued because of the presence of PhD students and postdocs and various other continuation of some of the activities in the past. And this was also the time when people started interacting with the external world, getting certain information as well as certain technologies to create our own experiments. And so negative ion-based R&D, for example, collaboration with IPP and others, or there were a lot of experiments on setup of facilities. I have not a picture here of Samir's high flux facility or the other facilities that they set up for development of materials as well as for testing. So in beta, the point here is that beta does not have plasma current. So it has only the toroidal field and it has the vertical field. So how is that a tokamak? It is not. But it is certainly what you can say is edge of the tokamak in some sense. Okay, so there were many interesting experiments, and I think a number of people here are have far more expertise in beta than I have. But what I would like to draw your attention to was it was a creation of restlessness to get experience with toroidal system. So Professor Kaur used to be extremely pushy when it comes to once an experiment was taken. I remember I was sitting in his office at that time, and there was a call and some issue with Aditya was there. This was related to manufacturing. So he was so angry. I never seen him so angry. He shouted in the phone. He said that if you delay, I will sue you. These are the words that these were very interesting experiences that if to push that. And then there were teams which went to L&T. Godrej, I think, made vessel, and there were lots of problematic experience with coils. So Aditya and Aditya upgrade have transitioned from going to design, going beyond design basis, and going towards a this is a picture I really like because it has actually the first cut of a diverted plasma, or at least a nearly diverted plasma, on our campus. Okay, so upgraded Aditya brought in a new fresh air here. Then there is a new tokamak coming up, which is triple ST under different stages of procurement and assembly. So let me say that we have daunting challenges. And so here I now enter into another zone. So SST-1, superconducting magnets, long pulse operation, current drive, heat and particle exhaust. Those are the goals. And our main difficulty is to cool down the entire set of PF and PF magnets and to drive specific currents in those magnets. Because it's just not enough to just cool them, we have to drive those currents in them which we have designed, which we have thought. And I will tell you in a moment. And for that, we will need the right kind of power supplies and maybe the other paraphernalia, but that is something that we need to do to upgrade it, because that is its mandate. So what is the scientific feature of the SST-1 baseline? So let us look at this picture here. It took us, believe me, it took us several weeks to produce these pictures because there was a very low speed connection between here to the National Energy Research Supercomputing Center, CRE, in, I think, Lawrence, Livermore. And they had given this login to Srini, and when we completed our certain preliminary studies, we started from here. So it used to be something like this. Two persons are always needed. Okay, one person will count how many keys and how many space bars have been pressed. Because once you press something key there, it will not appear on the screen. Okay, you have to wait. So all that has to be done, and the command has to be typed once correctly, because it will take only after a week we will know. So it was a very careful exercise, I would say. So there were times when, weeks and nights went. But why this? And so that is the importance is that this gave this frustration. I will tell you, the best resource you will have today is the frustrated PhD student. Okay. Unless you have them, you can be sure that you will not make progress. Because, and in a good way, okay? PhD students, take care. So important thing is discovery of the internet. Okay. The problem with the Volkswagen engine, the whatever let's say call it corruption, the discovery of the shale oil. There are a whole lot of things. The what is called what do we call that net connecting computers? Beowulf cluster. Extending the DARPA protocol to TCP/IP protocol. So many things happened only because they wanted to create something, there were limitations, and they were reacting to that. And so Srini said we must build our code, and there were pieces of that code in various forms, and it was built. What I am trying to show you is two cases here of why I am showing you this kappa and Li. The Li is an index of how sharp is the current within the plasma. So we have taken a 0.75 case here and a 1.4 case, so two very broad cases. In the case where Li is large, the current is concentrated mostly in the central zone, and therefore it is very hard to pull this plasma. Mute, please. It's hard to pull that plasma up by the diverter coil. So if you do that, you will get a structure like that, what you see on the right hand side. And as you pull it with great strength in the diverter coils, you will see all parts of it also touching the passive stabilizer. So the plasma hits the passive stabilizer in one case, and in the low Li case, it is extremely hard to bend the plasma's flux contours towards the diverter at an angle that we want, because we want the spreading of the heat. We don't want the diverter to be wetted only at a particular point. So because of that, you have two extreme cases. And so what happens is that you actually get a cube, a designer's cube, which is basically telling you on the three axes of internal inductance, which means how concentrated is the current in the core, kappa, which tells you the elongation of the plasma, and beta P is like the current, let's say, in the plasma. It's a ratio of the plasma pressure to the magnetic pressure, but calculated from the colloidal field. And what you will see as a body diagonal to the tube at the bottom, 0, 0, 0, let's say the origin, is you have a lot of heat flux on the diverter when you go to this case with low Li and low kappa, and that is if we want insist on low Li low kappa combination, and you get a high heat flux on the passive stabilizer if you insist on high Li high kappa. So once you start mapping that, you design a boundary that this is how I will design the reactor, because this was important. At that time there weren't much technology there. It was something simple. Srini will take a printout of the flux surface on a transparency paper. Samir will come from the other side and we will hold this against the tube light like this. He will draw the diverter plates. So Srini will put this flux surface and then they will try to match, and once they are agreeing on, then we will do the adjustment. The tools like CATIA and the integrated AutoCAD came much later. But leaving aside those sweet interactions, what is important is these were the equilibria that were used, the fiducial equilibria. They used to define the SST machine. Everything originates from here, which includes the ohmic simulations, the induced voltages from the coils, how much coils, whether they need forward voltage or reverse voltage, whether peak inverse voltage will be protected by this way or that way, what should be the power supply state on or off, all that detail was there. Those calculations are there. They were done, and they were done pretty painfully after a lot of work, after the design, which means I'm talking about beyond 97, 98. So it has a strong baseline. There were tools developed, people developed. So if we get the experimental data, it's possible to do the analysis. There are analyses which are related to stability and what kind of profile this is, and whether this has a stability to ideal modes or not. The interesting aspect of this is that how fast will different tiles of SST-1 saturate due to the particle flux is another important question, because you need to know what is the wall saturation time, and that is when the change in the density control happens, because then the plasma and the plasma wall become very social and your external controls don't help at all. Now here is a space of parameters which SST-1 can access, and the yellow dots are telling you where is the position in the international scenario. If you see rose star, then it starts at the center. In the new star, it is at the center. But you can see that in the n by n green wall or T by Ti ratio, which are the two most important factors today unknown, even today, it contributes definitely and differently to the current data because of its unique aspect ratio, because of its unique character, design character. It has a 5.5 aspect ratio, which is largest in the world, and it has a high kappa, which is around almost 1.8. So this kappa A product is almost 11, and this is not a product which any tokamaks have, and this causes the SST-1 vertical stability to be extremely challenging job. Indranil here knows that. He has a thesis on that. So the oscillations of those plasmas are fast, and they are fast, therefore they give you more AC losses on the superconducting coils. So you have a test bed which is not so common. Okay, so you can rejuvenate that. And let me now come to a rather funny part of this. Why is it a unique project? As Pramod said yesterday, fabulous talk, Pramod. The SST-1 sanction happened, and there were a large number of students taken. I think over the last few years, we had a number of PhD students available, and I think some unique idea must have arisen that why don't we? But these students were what? They were actually research students. they were given a problem and they were going through the references and then trying to find out uniqueness and trying to solve their problems. So this approach immediately got imported into a set of challenges SST-1 had, because no one had an idea of how to build that kind of a machine. First of all, we had idea of vacuums, high voltage, okay, but superconductors, cryogenics, there were lots of other things. So this force made a tremendous difference to that, because in a few years it was possible to develop the specifications and get them reviewed. And so very unlike any project where we have we recruit people and then we train them and all that, this was a case where the management had less idea and student had even less idea, yet they had an approach which made a huge difference. So it remained a very interesting situation, because what was presented by them in those meetings used to be listened with great interest, as if it was coming to you for the first time, because there were series of papers which were summarized, like what did so and so do to solve this problem. So let me come to this particular point where we deal with weakness. We are now changing the mood of the discussion. So let me become an English professor for a minute. Okay. So what is weakness? Okay, so weakness is a term we use when we know what is to be done but are unable to do it ourselves. It is not ignorance. Ignorance is when you don't know what to do. Okay. But weakness is a case where you know what to do, but someone is not letting you do it, or you don't know how to do it. I mean, you can't do it because of some restrictions. Let's say you are weak, so obviously you cannot get up from the bed. Okay, that kind of thing. But you certainly you need to get up from the bed. Okay, so what could be the root causes of this? In my view, there are 4 causes. We are not fully convinced, so we look for support. A sentence from a colleague or someone, सही चीज़ है, यही करना चाहिए, यही करना चाहिए. So you, आपकी श्रद्धा जो मजबूत करते जाए. Now you would like to do, but you're strong. You want to rely on a few shoulders. Okay. दूसरा है कि we are convinced. Okay. But our higher ups are not convinced. Common problem everywhere. Okay. And now, so we either give up or we try to find a golden mean. ना तुम्हारी ना मेरी, हाँ, थोड़ा सा हाफ वे चलेंगे, फिर थोड़ी देर के बाद में शायद हृदय परिवर्तन हो जाएगा. Okay, so अब लगे रहो. But if you are right, it's a good thing to do. Okay, if you are clever and you are devious and plotter and planner like the TVCS, then it's not a good thing to do. So presumably to change perception and to change obtain support, you may have to go on an in-between path. But internally you must be convinced that what you're trying to do is right. It should be on a foundation of, let's say, selflessness. It should be based on a foundation of selflessness and truth. Third case is, we both, which is that I am convinced, my boss is convinced, but we don't have resource. So, we wait for a while and try to obtain the resource and solve. Fourth is we both are convinced resource is also available, but the resource is not trained. It lacks project culture. It lacks quality culture. I mean, by quality culture, I mean that, if you leave the person alone, you don't monitor it, he still does a great job. We want that state, right? No one is going to observe you all the time. This will be foolish, because then one manager will be all the time watching you. Okay, so what do you want? You want the internal structure of that person to be such that the person automatically delivers a high quality. There is very little to monitor. That is the state you want. So Now, these are the weaknesses and combinations that one has to overcome. Now, my point is that the medicines are here. Okay. First of all, if there is trust, if there is mutual respect, if there's empathy, if there's honesty, if one learns to forget and forgive, otherwise you keep that in mind and then you don't move on, and then positions are strongly drawn, and that will create those core values are very crucial for anything to happen, because many times major projects have suffered simply because of lack of cooperation between people, and then no one bothers. That state should not happen. Teamwork is critical, but again, English professor would say, to know exactly what and when the other team member needs, pass कब देंगे उसको जब गोल होगा ठीक से, that you should have an idea, you should give that pass and you should be working for it. Okay? So दूसरा है कि replacing blame game instead of blame game. This is a classic example कि पाइप टूटा, suppose लीक हो रहा है तो सबसे पहले आदमी का नाम, वही रिस्पॉन्सिबल है, इंस्टेड ऑफ फाइंडिंग आउट कि वो खराब हो गया था, क्यों खराब हुआ था, उसकी रिस्ट्रिक्शन क्यों नहीं होती. रूट कॉज वुड नॉर्मली गो टेक्निकल, बट इफ यू आर एट ए CMM level 0 something, you will be always looking for a person, because it's very fancy to find accountability before doing the root cause. So that is a mistake. Collaboration. Areas where we don't know something, there we will have to collaborate. Otherwise, we cannot grow fast. Okay, because the other person will also get something from you. So, critical. Collaboration, very critical. And finally, recognition. You take lots of small steps towards this. And here I want to tell you that remember that in the SST-1, you might blame magnets, but it is one of those things that has worked extremely well. For hours together, those magnets can perform, PF magnets. PF coils had come after fabrication, and they probably were in the room here. I don't remember now where they were kept, and it was a hot afternoon, and there was a bit of a, I think, let's say, hot exchange between certain high manager levels. I was not there at that time to notice that, but I was called. So we had organized a biscuit and tea in that room, and Professor Cow had come, and it was extremely hot. I mean, he was sweating all the way. There was no fan, nothing there in that room. It was just kept there, and Professor Cow made a very nice speech there. He said that this is one of the items we have received for SST-1, and Professor Saxena had shown that it has been made to the way we wanted it. This was actually seen and noticed, because you will see photographs of Professor Cow in the factory also in some of the old things. But the point is that he made a point that anything that you do is going in that direction. Make sure that I mean, it's not just for the motivation of the person, it is a collective expression of that you have gotten somewhere, and that helps you to keep that momentum going. So if we just get into who's responsible for what, we will never go anywhere. We have to find what steps need to be taken to give us a machine which is of the same quality which our, let us say, our peers, internal peers or ITER partners have. Okay. So restless creativity should become the second. And here again I will say that everyone must constantly think over what is that one can do, what difference one can do, to think creatively, because otherwise most of the time we'll go in analysis or analysis about someone or someone's opinion. Believe me, these are thoughts which will only kill time, and it's extremely crucial. The more you get attached to this creation, the less clutter there will be in the mind, and everyone will be happy. It will solve all problems. It's not true only for workers, it's for everyone. Everyone must be creative and ask, what is a new thing we could find today. So let me come to a history of ITER and Inter India here, uh, because this takes us in the direction of collaboration, and you know this very well. So this is 2003, where we see the civil nuclear dialogue happening, the discussions with the US, and so on. And there are some notes I have in those times. No, we joined in 2005 December, but you can see that this is a page I randomly found. This is 21 August 2003, and about 2 years back. And you can see here uh, what are the areas of contribution. Professor John was sort of shepherding this entire proposal, so he was asking everyone to contribute, and we were taking notes, comments from Vasu, Kulkarni, Bora, John, Ujjwal, then again some points by John. So we just kind of noted that down. Then another meeting, I am brooding over, we should have a preliminary meeting with ITER experts to assess what exactly they need. I mean, there are so many things. Ujjwal is asking, are we competing in the hardware? YC Saxena says yes. He gave specific example. So I am trying to tell you that 2 years before, or probably year before that, uh, there has been an internal deliberation, regular meetings here. People thought what they can do, what they cannot do, whether we will be able to manufacture, we will not be able to manufacture, and so on. And this is 2005 summary of the status report. And here you can see Professor Kaur prepared a report on the behalf of IFRC, reflecting members' views, and you can see that fusion fundamentals with ITER is a possible partner in the realization of self-sustainable burning plasma. Then the importance of socio-economic aspects, and finally that report addresses the topic of plasma physics to assist it in understanding the achievements of better coating, cheaper light sources, improved heat resistant materials, and other high technology. This last line has a extraordinary importance because it will actually start cutting down the mute please. I am hearing myself. I cannot mute myself. That's a bit hard. Recording also?
Hello? Please mute.
Recording is playing by itself. हाँ 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 Agni was not there. हाँ, okay. हाँ मुझे बकवास बंद करना पड़ेगा ना जल्दी. कंट्रोल. उनको बोल देंगे. Can you please mute? बोला आपने? She cannot mute. We cannot mute. She cannot mute. Okay. So let us ask people to keep their mobiles away. ठीक, चल अपना ये लगा दो. Okay. So I was here and I pointed, draw your attention to the applications, and these are important parts you will see towards end. So there is a long history of research that has brought a strong basis to it. And so here is a quick shot at the Cold War era. There are some interesting documents there, like how the agenda was initially not including ITER, and then how it was, tactfully introduced into the meeting, and how these people came out and went in, Gorbachev going in, etc., etc. But let's leave that as interesting history there. So there was a meeting, then there was a withdrawal from US earlier, but then it rejoined, and then do notice that it joined after this China and South Korea joined. Then Cadre site was agreed. This agreement means that actually this ITER, many people may know there are two agreements here. One is the ITER agreement, that is what is called a BA, or broader approach. In the broader approach, the Japan will set up a fusion materials facility, and it is going in that direction. It has a high-tech engineering materials validation center, and that accelerator, those systems are also built by in-kind contributions. There are a number of deliveries from Spain, from France, from Germany, etc., which have gone there in CA to either making magnets or cryogenic equipment and so on. So I will now come to the this TBM history. So here, when ITER was joined in December 2005, there was an email from Valery Chuanov, who was the chairman of the test blanket working group, and it was directed to Professor Kao, saying that would India also like to join TBWG. So at that time, no one knew that there was another thing, something like parallel to ITER. So Professor Kao asked us to find out. So I and Rajendra Kumar had gone there, and then we saw what they were doing. They had lots of structure there. In fact, they were interacting for a very long time with each other, the other members. So they had certain exchange of experimental data. They had set up some facilities, and they had developed some materials. And so to join the TBM program was the invitation. And so Professor Kao then asked chairman on organizing a meeting of the experts in DAE, and there was some feeling that this is a program one can do with help of DAE. And there was a problem because there were 7 partners, and there were only 3 ports, and 3 ports were divided into 2, so there were 6 slots. And the problem was that there are 7 interested members and only 6 spaces. So at that time, it was decided that either India brings a design which is reviewable and something novel, otherwise the ports goes to US, because US was already established. So we had gone to Chennai, and in IGCAR we met Dr. Chellapandi. Then there was a discussion, a new idea of mixed solid and liquid TBM, where mixed concept was proposed. Rajendra Kumar thought over it, and then it was developed. Then it was defended, and there were a lot of criticism, and there was a deadline for review. So in April 2008, it was to be presented. So a team of people from IPR, I don't have the photo here, and a large team had gone there to present that, in different aspects were presented: materials, coolants, heat transfer, mechanical, structural, regulatory, everything was presented. Design basis and beyond design basis event. IGCAR had done an absolute fabulous job in reviewing, and so also in BRC. In fact, Dr. Vyas and a few others used to sit in those reviews, and there was a team here, engineering services team, which had developed those designs. So a program was started, and in fact, those guys did not believe it at that time. There was a meeting in which Professor Kao was there, Professor John was there. He was the member of the ad hoc group, and there were people from European Union who were not willing to take this on board because they said it is too late, etc. So they had their own ways of saying no. And so Professor Kao said that our experts in DAE are saying that they can make this material in a couple of years, and they actually said it's not possible. But it was actually made in 2 years. The RAFM, the reduced activation ferritic martensitic steel, was made with the help of Bidani and then DMRL and a few other people. So then of course this was, plates were made, there lots of developments here, you know it more than I do. And similarly, there were functional materials which were basically lithium titanates, although beryllium we did not make because beryllium was to come from brick. And then there were developments in the PBLI, which I don't have photographs, but now of course our people can make the PBLI ourselves also. So that time this liquid metal concept as well as solid concept were together, and both the programs had to be started. So hydrogen sensors were made, there was a fuel cycle development, there was a development of the entire back end of the TBM to ancillary units all the way to heat rejection cell and so on. So this led to a number of interesting developments. This is a very, let's say, call it nostalgic and a mail that we all of us cherish, because we had written to Professor Kao that finally our concept has been accepted in 2008, and he said he had done a great job. So we had preserved this mail. So it was a good certificate for us. Let me now come to the technology that we do a part on ITER, but there are certain things we don't do. And so in each of those red areas, now where do we really want to go? So let us make a sort of list that if we, which considerations would go into future power plant. And these are very simple, let's call them kitchen questions. So it must produce net electrical power, obviously, and it must do that over a period which is such that the sale of the power covers the investment cost, okay, and allow probably another plant to be built from that revenue. Then it must adhere to the norms of public safety, environment and occupational safety. It must be competitive with other sources, because there will be other competing sources, and it must comply with the grid code, which means that for a certain number of days it must not fail. It must assure this electricity will be provided. So this is a stage which NPCIL goes through every now and then, until they do the 75 days or 50 days or a month long steady supply. They are not paid at a commercial rate by the grid. Power Grid Corporation is going to buy the electricity, and you have to assure them that I will not fail in a stretch for say 70 days or 100 days. Till then you get only 1 rupee per unit, and only after that you start getting 4 rupees, 5 rupees, and so on. So, and then of course they sell it at different costs. So practical questions are, what are the costs of such a plant, and how will they compare with competitors? There are papers on this, okay? Then how fast can one build? That depends on what is the readiness of the components. Because if you had central stores, if you had all the components ready, you could have probably built them faster. Performance reliability, how many days in a year it will be available, how soon it will restart after emergency shutdown, what will be the basis of confidence in investment by the private industry. If we ask industries to invest, why will they invest? There has to be some confidence. They should have done something like that before, okay? And what is the role and authority of the regulator? What can he stop? What can he start? Where we need approvals? What is the role of the operator and responsibility of operator? And of course, of the design owner, who will be finally held and accountable, etc., in case there is a problem. So industries are very cautious. They cannot commit more than what they are liable. So you cannot have an indefinite liability. So there is a whole world called nuclear liability, and there can be problems. One of the, let's say example, or rather dark and morbid example of this is the Union Carbide. Okay, lots of people died, and we don't know what was the liability, who should have covered this cost, and why and when and how much, and what rule structure was existing. But we don't know. Maybe the serial has some facts which you know. So there is a structure here that needs to be clarified. So now, if you want to go in that direction, you have to see back a glimpse that in the early days when we had just gained freedom, there was nothing, right? Everything was starting from the scratch. There was no material, there were no tools, there were no buildings, there was nothing. There were not people also. So we have to start everything everywhere. It's a greenfield project. Atomic energy is an example of that. Okay, everything had to be made in-house practically. So, and imagine the spirit in the wings of fire by Dr. Kalam. There you can see some sentences like this. He says that in the pursuit of their program, कि जहाँ लेटर भेजते चाहिए था, लेटर से वहाँ तार भेज देते, और जहाँ तार भेजते वहाँ खुद ही पहुँच जाते. The urgency of getting things done and the passion behind it was so much that people would, throw themselves at the problem in full swing and just somehow get it done. And so the proactiveness, which is one of the major, let's say, concerns and problems, needs to be seen on that context. So if fusion energy for commerce is going to be a long drawn program, okay? So you have to hold your ground, okay? You have to do your bit, and you have to stay alive, because there is going to be problem, there are going to be scattering, okay? Now rockets have been built by a number of experimenters. If you look at the rocket program, and fission reactors too have been built after a number of trials and experiments. It's in that process that one has developed various technologies, and fusion too will have its own trajectory. It is just another technology on the horizon. So if we does it take that long? So this is a picture I took from a flyer which was developed during Vikram Sarabhai's contribution celebrations. You can see that this is a journey which, fission reactors and research reactors, and it's over many years. But in that process you can see, water technologies, sustainability, healthcare, agriculture, industrial applications have emerged. So the program needs to remember that these are the byproducts. These byproducts, if they were becoming the focus, the program would have been totally different. So the trajectory must remain the same, and all good things will come out of it. Okay? So one of the most challenging parts that this new generation is going to face, and has faced earlier too, is ridicule. ये तो हमेशा 10 साल लेट रहता है, ये तो कभी बनने वाला नहीं है, ये तो अभी पता चला है कि ये डिज़ाइन ठीक नहीं है ना. हाफ इंफॉर्मेशन, मिस इंफॉर्मेशन, आर्म चेयर रिमार्क्स, half cooked information, lack of knowledge, and that kind of thing will start create. That's a fertile ground for these beautiful remarks. Okay, there are many. I have 184 articles on fusion physics. None of them make sense if you talk scientifically. If they had some sense in them, we could have still taken, because all of the physics and technological challenges that we know are already known to us. There is nothing new futurism is saying. Okay, so there will be bitter remarks, politically motivated criticism, okay, sarcastic remarks, and lots of other irrationality, which you will encounter in public life, private life, corridor remarks, travel, bus, airport, going in plane, etc. Everywhere. Everyone will, approve the proposal, but with a remark. So you have to stand ground. You have to stay alert, because this is common. Interestingly, this is very common, and it is just used by people because they don't have anything other better things to say. So to create a program, we must use something that acts as a guiding light, something that crystallizes the random thoughts into an order. Okay, and a fusion reactor, power reactor that bridges the gap between ITER, which is basically a physics demonstration of fusion energy, to a power reactor where lots of blankets and fuel cycle and so many things are there. That reactor is important. That reactor is going to set goals before various technical teams, which means diverter team, your fuel cycle team, your let's say magnet team. These people will derive their specific targets out of a program, and these targets can be of this kind. This just like, for example, one could specify the magnetic field a coil should produce, how much field it can withstand, how much dB/dt it can withstand, what stresses it can withstand, how much should be the resistance of the insulator resin, things like that. So plasma current, size, shape, heat and particle fluxes, radiation loads and load combination, like how much weight, it's structural, seismic spectra. Okay, then prescribe behavior of material properties, like what should be a behavior of, let's say, an electronic circuit when it is exposed to gamma radiation, or what should be the behavior of, say, tungsten or something when it is exposed to radiation, what should be the ductile to brittle transition temperature trajectory. So there could be these specifications. So what I'm trying to say is that no matter how far that goal is, your tomorrow's activities are unchanged. They are still aligned to movement on a trajectory, and it's probably a long drawn idea. So here is something, let's call it an important graph that gives us direction. Okay, now what I am showing here is, on the x-axis is the radius of the central solenoid, the inner radius of the central solenoid, and on the y-axis are the number of turns in the central solenoid. Okay, and basic physics, you cannot violate. So it's going to tell you which direction to go. You cannot fight with that direction, and whichever direction you take is going to decide your strategy. So you have to decide directions first. So where are we deciding directions here? Imagine a long solenoid. Within that, the field is constant. Outside field is zero. Imagine a set of solenoids inserted within each other with a certain thickness, an inner to outer radius. So we have a thick solenoid. And how much flux can it hold? So on the right hand side, on the right hand side figure, you can see the dashed lines are telling you how much stored flux it can have. And this flux is what you would like to use in driving the plasma. So if you have a small solenoid, let's say of the order of a meter, okay, with inner radius, you can at best go to 50 Webers, etc. But that too, if you go to something like 12 turns on the green horizontal line, and you see there you have 15 Tesla written there, which means that we are asking the the the, the conductor to withstand that. That's not possible at the moment. From what I know from Upendra, it may be around 10 or so. So if we are looking for that kind of a field, then obviously we are somewhere between this 5 Tesla line and a 15 Tesla line. So we bracket ourselves to this direction. And within that, now let us ask ourselves, how much time does it take for a blanket to become hot enough to give you power? So if you take the materials properties and take the worst case estimate, you will get something like a few thousand seconds, maybe 2,000 to 3,000, which means that you need to have a pulse which will last for at least 2,000 to 3,000 seconds. It's only then that the blanket will get hot enough, and then only you will be able to extract power out of the blanket. So clearly, if you want to drive plasma current by ohmic, then you must have a flux that will last for 1,000 seconds or at least 2,000 seconds, which means that it should be more than something like 500 Weber, certainly more than 300 Weber. Okay, so we are already talking about a radius of the solenoid, inner radius of the solenoid to be 3 meters. So inner radius 3 meters plus the width, add some width to it, and that's where the TF will start, then TF, then plasma. So where will it go? So there is no doubt that if we want to do ohmic driven reactors, we will have to go for large reactors. Okay? A large reactor size is a natural consequence of choosing the ohmic current drive. If you instead do non-inductive current drive, maybe you don't know today, but you do it tomorrow. Okay? You can come to compact reactors, cheaper reactors, better electricity cost. So you have to think which way we want to go, because that's a very different direction. This is a very different. If you start building a reactor of 9 meters, you know what its cost will be, how it will be funded, how it will be supported. We have no idea. So it's very important to integrate the power considerations, which means that the blanket must be warm enough to give you the power that you need. And that takes time. And for that, you need to drive current up to that point. And for that, either you choose ohmic, make a big reactor, no issues, or make possibly a compact reactor. So an outstanding physics issue is still there, which SST-1 can address. So there exists a relevance of these machines, provided they are built properly, that unless we choose large size reactors and accept dynamic fatigue of the central solenoid, we have no option than to choose non-inductively driven reactors that are related. So we have to make a decision. We cannot imagine that today we will make an ohmic reactor which will last for 1,000. It's not going to. It's not going to be there. You cannot make small reactors. You have to start with the radius which is something like a couple of meters. And this is basic physics. This is classical electromagnetic, 12 standard. You cannot cross it. Okay. So you don't need rocket science there. Now, what are the demos targets? high tritium breeding ratio, reuse of the fuel, sustained demonstration, power conversion and connection to grid, reliability of performance, and so on. So these targets, along with tritium breeding, okay, need to take you to a program which you need to make happen. Okay? So we know the goal, there are gaps, and we need to achieve a lot on the non-fusion plasma, hydrogen plasma. We have not reached to a level there that we want. And secondly, there is very little experience in the DP fusion anyway, even in the world. So obviously we have not there anyway. The problem is the test facility for a reactor is the reactor itself. So you have to build the reactor to test. This is a chicken and egg problem of mine. And so when we have a long program, like the kind of space or fission, it needs to be drawn from that perspective. And so we should define a stage approach for that. So what is the stage approach? We can think of demo being built after a model pilot plant where you try everything, all aspects of it. And pilot plant is also a very big thing. So we need to have a smaller device where do testing of technology. And for that we have to do R&D. So we ask the demo, what should be the shape of the pilot? What features should it have? So we are going now top down. Demo tells pilot, okay, this is what I would like to be, and will you test that? And then the pilot correspondingly translates them into smaller level target goals, but not fully nuclear like pilot, where it defines the systems. It defines integrated performance of diverters or magnets or joints. It specifies heating and current drive scenarios. We are doing at a non-nuclear phase in the beginning. And then the FAST, which we call Fusion Engineering Science Test, facility defines what should be the R. So this is the top-down hierarchy. And then outcome of this should be, the R&D tells the FAST what can be actually achieved. Which joints, which magnets, which material to be used, which will rely for a long time. Also, it confirms integrated performance, like if you do LHCD or fast wave or whichever RF driven current drive, and what efficiency one is getting. Okay, and finally pilot gives you a feedback on the demo design. What is a realistic demo design you can choose? So if you do in a stage manner, you don't commit yourself fully. It's not that all the money is lost. You go in a stage manner. You build on top of what you learn, because you will keep a room for changing design. So with that, the path to demo needs to look for compact, cost-effective solutions. It needs industrial involvement, and it needs the flexibility to adopt emerging technology. And the important point is we need to learn from ITER the processes and the techniques, the intricacies of manufacturing, and certain high-tech items that we don't have. And then we need to establish a wide network, sort of pan-India network of creating centers for excellence where certain pieces and certain systems can be made by those entities, including industries. So there are, you can say, 4 phases with specific outcomes listed here. So the first, which is the, let's call it the star performer, is a 25 megawatt machine, which is basically technology enabling. It's long pulse, non-inductive current drive, and its job is to qualify technology. And a machine like FAST, which is a crucial decision-making step, is the first thing we need to make. And this will tell us which way we should go. Do we need magnets with joints? We don't need magnets with joints. Do we use the current drive or we have to abandon that completely? So it's a, and this is a thing, this is like you can say JT60 like device, which is going to pursue high beta plasmas and long pulse operation, something that we have been thinking. So it's already there. So we have to rise to a level where our people, our systems are also matching other systems. In the pilot plant, which is kind of 200 megawatt, the key point is, can one deliver power, electrical power, to the grid? Why we need to do that? We are saying its QE is 0.5 to 0.5. Why do we want to keep QE 0.5? Because at smaller scales, which are talking about 2.5 meters, 3 meters, it's not possible to get capital Q more than 5. It's not possible, because simply because the scaling laws do not allow you. H mode scaling laws will not allow. As soon as you try increasing beta, you will have lots of losses. So we have to play. Why do we want to do this? It's because we want to understand a pulse of 3000 seconds can be produced. It can be absorbed in a, let's say, energy storage system. It can be re-delivered for generating steam. The steam can drive turbine and actually connect to grid. And that we satisfy grid code for 75 days, we can produce in an uninterrupted fashion. And that is the beauty of the pilot. It will give you a basis to you, to industry, to university, that this can be done. You just need to scale up to them. So that is the crucial, because otherwise if we will not be able to know the costs, we will not be able to know the time schedules, we will not have experience to build them. So a pilot is a crucial part. No matter, it takes 300 megawatt from the grid and returns back 160, it's okay. It is still doing a good job. But it should tell you, an industry, a lot about how systems operate and how reliable they are, because there can be so many faults. So to summarize, we must remember the roots and the legacy, to remain steadfast on the goal of fusion. The goal of fusion research is to build a capability for a fusion power plant. Precise targets can be derived from a stage approach. An integrated test facility is essential. A non-fusion advanced tokamak is essential to train our workforce. And an organizational project culture that is able to carry out design, procurement, construction, commissioning is essential as per time and policy. So we go back to the beginning. So what is the beginning? We go back to the primordial fire. Look at the periodic table again, different. You see breeder, multiplier, superconductor, wall conditioner, coolant, diverter, heat load, detector, multiplier, cables, insulators, tritium storage, martensitic, austenitic seal, bolting material, everything is there. And so that's what it is saying. Thank you. Thank you for listening. And incredibly long, and I'm absolutely pleased that I did not have to wake anyone up. But I am glad that I could say this. I don't know whether Raj Singh has any kind of question and answers, but there is.
So, first of all, I would like to thank Professor Deshpande that he tried to download all his 40 years of experience or 40 years of association with the plasma, and I'm thankful to you all that this almost around 1 hour 50 minutes or more than nearly about that you all listened to that, and I'm sure you must have got one thing or other out of this talk. No one can say that I have got less. I think such a nice, beautifully planned talk, starting from beginning till end, and all aspects, technical, physics, managerial, have been covered in that. You are really thankful to you, sir. So now is a
Thank you.
session for question answer. If you have energy left in you, you can you can still ask the question. Anybody? Or if I, huh?
Last question.
Sorry, giving back. So, if no question, then I can request Dr. Nema to present a small memento to Professor Deshpande.
Thank you, Raj Singh.
This reminds me basically in the beginning when you joined IPR, we used to have a talk in that what do we call it? That big meetings, Professor Kao, Professor Mattu, they ask question, and so that long session, the same, it's like that only. Thank you. Tomorrow we will have talk at 2 p.m. from Dr. Arun Chakravarti.